All right, in this lecture, we're going to finish our section 3.4 material on partial fractions. And a quick review in the first parts of this section, we had seen that the method of partial fractions will be used to integrate rational functions where the degree of the numerator is less than that of the denominator. And we proceed by seeing what form our denominator takes after it's been factored. And that will tell us what the partial fraction decomposition looks like. However, not every rational function has the degree of the numerator as less than the degree of the denominator. That was one of the assumptions we had been working with in the first parts of this section. So in this last part of the section on partial fractions, let's consider the case that the degree of p of x, that it is the numerator of our rational function, is greater than or equal to the degree of q of x, which was our denominator. So in this case, we must first perform long division to simplify the integrand in order to get something involving a rational function where the degree of the numerator is less than that of the denominator. So when we're integrating rational functions, the first thing we always want to look at is whether the degree of the numerator is less than that of the denominator. If so, we can proceed with a partial fraction decomposition. However, if not, we first need to perform polynomial long division. So let's look at some examples of this. In this first example, we're asked to evaluate the integral of this rational function. We can see clearly it's a quotient of two polynomials. However, in this case, the degree of our numerator is 3, and the degree of our denominator is 2. That is, the degree of the numerator is greater than that of the denominator. So using long division, let's see if we can simplify our integrand. So here we're trying to take our numerator, which was x cubed plus 2x squared plus 2x plus 11, and divide it by the polynomial in our denominator, x squared plus 2x minus 3. So when I compare the lead coefficients of these two polynomials, I ask myself, what would I need to multiply x squared by to get x cubed? And that would be x. So taking x times this denominator, x squared plus 2x minus 3, I would have x cubed plus 2x squared minus 3x, and I would then subtract that value from our numerator. So this would leave me with a 5x plus 11, and then when I compare my lead coefficients of these polynomials, x squared and 5x, well, I see that x squared now has a greater degree than this remaining term, 5x plus 11, so I can't divide any further here. So our integral that we started with can now be simplified as this term that we had, x to the first power, and then I had a remainder of 5x plus 11 over my denominator, x squared plus 2x minus 3 dx. So the first term in this new integral, x, I know how to evaluate directly, and this second term is now a rational function where the degree of the numerator is less than that of the denominator. So for that second term, I can make use of partial fraction decomposition. And the first step there would be to factor the denominator completely. So this second term, 5x plus 11, can be factored over x squared plus 2x minus 3, has a denominator which can be factored as x plus 3 times x minus 1. So trying to decompose that second term, we're going to take 5x plus 11 over x plus 3 times x minus 1 and look at its partial fraction decomposition, which would have the form a over x plus 3 plus b over x minus 1, since our denominator involved distinct linear factors. So simplifying this equation by multiplying through by our common denominator, we have 5x plus 11 is equal to a times x minus 1 plus b times x plus 3. And since I'm working in the case of distinct linear factors, I could solve for a and b by choosing specific values of x to simplify my equation. So for instance, if I wanted to solve for a, to kill off this b term, I could take x equal to negative 3. So if x were negative 3, then the equation reduces to negative 15 plus 11, so negative 4 would equal negative 4a. And that implies that a is 1. Now, if I'm trying to solve for b, if I want to kill off the a coefficient, I could choose x as 1. So if x is 1, then my equation becomes 5 plus 11, or 16, is equal to 4b, which implies that b is 4. So, looking at our integral in its decomposed form, we'll recall that we had initially one factor of x, and then for the second term, our decomposition has the form 1 over x plus 3 plus 4 over x minus 1. And so our antiderivative is 1/2 x squared plus the natural log of absolute value x plus 3 plus 4 times the natural log of absolute value x minus 1 plus c. So here we see that in the case that our numerator has a degree that is greater than or equal to the denominator, we would first need to perform long division to simplify that integrand down to the sum of some polynomial term and a rational function where the degree of the numerator is then less than the denominator. And to integrate that remainder, we could make use of partial fraction decomposition as we did in our earlier examples. So let's look at one last example here to illustrate the case of long division. So in this last one, we're asked to evaluate the antiderivative of this rational function. We can see clearly the degree of our numerator is greater than that of the denominator. We have third degree over first degree. So we need to begin by performing long division to simplify this. So here, using long division, we're taking x cubed plus x and dividing by x minus 1. So comparing the lead coefficients, I ask what would I multiply x by to get x cubed? and that would be x squared. So taking x squared times x minus 1, I would have x cubed minus x squared. And subtracting that from our numerator, I would be left with a positive x squared plus the x to the first term that we had. Now comparing the lead coefficients x and x squared here, I would need to multiply x by a positive 1x to get x squared. So taking x times the x minus 1, I would have x squared minus x to the first. And subtracting it from our previous remainder, the x squared terms cancel, and I would be left with 2x. So again, comparing those lead coefficients, in order to get 2x from our x to the first power, I would have to multiply by 2. So 2 times the x minus 1 would give me a 2x minus 2. And subtracting that from our previous remainder, the 2x terms cancel, I would be left with 2. And now x no longer divides this constant term, 2. So this would be our remainder. So after performing long division, we're left with x squared plus x plus 2 plus my remainder 2 over x minus 1. And once I've performed this long division, well, I know how to integrate this function directly. We would have a 1/3 x cubed plus 1/2 x squared plus 2x plus twice the natural log of absolute value x minus 1 plus c, since this was an indefinite integral.